Okay, good morning. Today the revision class for Unit 1 will be oscillators. Okay. Oscillator working principle is positive feedback. Okay, oscillator is an electronic circuit produces a AC wave signal without applying AC signal as an input. Okay, see the block diagram. We didn't apply any AC input signal, but it can produce AC signal. Okay, and block diagram of the oscillator. This is a block diagram of the oscillator. Now, for block diagram of positive feedback, if we take this is the amplifier. If we have the feedback is positive feedback, what is meant by positive feedback? VF and VD both are in phase. Both are in phase. Okay. Now we know that both are in phase. VD is equal to VS plus VF. If you find out the closed gain feedback, closed gain feedback or positive gain feedback, AF is equal to, we know that for this total circuit V naught by Vs. For this particular amplifier, V naught is equal to open loop gain. Okay, this amplifier only if you consider without feedback A. Okay, for this amplifier, output is V naught, input is Vd, and gain is A. Then A is equal to what we can write V naught by Vd. And for this feedback network, gain is beta, input is V naught, output is Vf. Then we can write Vf is equal to beta into V naught. And Vd is equal to, I already said, both are in phase. That's why Vd is equal to Vs plus Vf. From this, we can write V naught. Okay, open loop gain is equal to V naught by Vd, right? Okay, V naught is equal to A into Vd. They are given equation numbers. Okay, equation 1 is total. Okay, closed loop gain with feedback. A is open loop gain without feedback, means only amplifier. And VD, VF, VD and VF, sorry, VS, this VS, sorry, VS and VF both are in phase, sorry, not VD, no, sorry. VS and VF both are in phase, that's why VD is equal to VS plus VF. Okay, now, first, I'm going to take from here V naught. V naught is equal to A into VD. Okay, in place of VD, okay, you can substitute equation 3, means substitute equation 3 in equation 1. Then we are going to get V naught is equal to A into Vs plus Vf. Then V naught is equal to A into Vs plus A Vf. Okay, substitute equation 4. What is equation 4? Vf value. We are going to substitute here. Then we can get A beta, okay, V naught. Now here V naught we are having, here also V naught we are having. Okay, send it to the left side. Okay, then V naught minus AB V naught. V naught if you take common, we'll get 1 minus A beta. Okay, overall gain is V naught by Vs. This Vs if you send this side and 1 minus A beta if you send this side, we are going to get V naught by Vs is the overall gain, or I can call it as a closed loop gain. Okay, here closed loop gain in the sense positive feedback amplifier gain. Okay, AF is equal to V naught by Vs into A by 1 minus A beta. Okay, this is about the field. Okay, closed loop gain or positive feedback amplifier gain. Okay, we know that AF is a feedback gain or closed loop gain. A is the without feedback gain or open loop gain. Beta is a feedback ratio or feedback network gain. Okay, now we know that in positive feedback, gain is increasing. In positive feedback, stability is decreased. In positive, okay, gain is increased, stability definitely will decrease. In positive feedback, distortion increases because P point is always going to change. Noise is increases, bandwidth will decreases. These all are the characteristics of the. These all are the characteristics. These all are the characteristics. Characteristics of positive feedback. Positive feedback. Okay. Now this is very important for 2 mark question. I will show to you. Okay, very important. Condition for oscillator or condition for oscillating the signal or Bark-Hassan condition. If they ask here, okay, magnitude of A beta should be equal to 1 to maintain sustained oscillations. Okay, or you can write this point, or directly you can write. Okay, if you not remember this one, magnitude in the sense I always take it as a mod. A beta is equal to 1. If you write directly this one, okay, answer is correct. This is the first condition. Okay, next the second condition. The phase difference between A and beta should be equal to 0 degree or 360 degree, or integral multiple of 360 degrees. Okay, the phase difference or the angle A beta is equal to 0 degree or 360 degree, or integer multiple n into 360 degree, n into 360 degree. Okay, n into n into 360 degree, integer multiple of 360 degree. Because right, in positive feedback, I already said that Vs and Vf, okay, both are in phase. Both are in phase. That's it. Okay, this is very important. You can write Barkhausen condition. Okay, A beta is equal to 1. Okay, or the angle or the phase between A and B should be 0 degree or 360 degree, or integer multiple of 360 degree. Okay, now types of oscillators. Basically, oscillators are divided into two types. Okay, two types based on shape of output waveform. Okay, that is feedback oscillator, relaxation oscillator. Okay, shape of, okay, how output we are going to get. Okay, feedback oscillators are called sinusoidal oscillator. Sinusoidal oscillator. Okay, because feedback oscillator generate. Okay, these feedback oscillator can generate sinusoidal waves. Relaxation oscillator also non-sinusoidal. That means relaxation oscillator generates non-sinusoidal waveform. Okay, examples are given. For feedback oscillator, example is sine wave. Here square wave, triangular wave, sawtooth wave. These all are non-sinusoidal. Feedback oscillator working principle is positive feedback. Relaxation oscillator work principle is capacitor. Based on the capacitor, it's going to be that. Okay, it is a on-time off-time will be that based on that. Okay, and examples of positive feedback is RC phase shift oscillator, Wayne Bridge oscillator. Here, square wave generator, okay, triangular wave generator, okay, multi-vibrator. These are the examples for relaxation oscillator. And this is based on the output we can divide. This is oscillator divided into two types. Okay, based on frequency now. High frequency oscillator and low frequency oscillator. Okay, high frequency oscillator. See, these oscillators generate, okay, oscillators generate greater than 100 kilohertz frequency. Okay, these oscillators generate less than 1 kilohertz. When it is greater than 100 kilohertz, definitely the application for RF circuits, radio frequency circuits. It is when less than 1 kilohertz, then it is a audio, okay, audio circuits. Okay, audio frequency circuit, or audio circuits. High frequency oscillator can use in feedback, okay, LC circuits. LC. Okay, inductor and capacitor for high in feedback. Feedback. In feedback network. In feedback network. This is low frequency oscillator can use RC. Okay, resistor and capacitor in feedback network. In feedback network. Okay, this is. And examples are here. We'll get Colpit, Hartley, Crystal, and the Claps oscillators. Examples are your RC phase shift oscillator and Wayne Bridge oscillator. Now first we'll discuss low frequency oscillators. Okay, or RC phase shift and Wayne Bridge. Okay, here the basic amplifier will be there. This basic amplifier we are going to use CE amplifier. Either you can use fixed bias or self bias circuit. Okay, for this CE amplifier, how much phase shift is there? 180 degrees will be there. Barkhausen condition we know. Okay, the phase shift between A and beta. This is A and beta should be 360 degrees. Okay, now see here 180 degrees will be there. Okay, in feedback, it is a low frequency oscillator, right? RC. Okay, RC components will be the feedback network, RC phase shift network. Okay, this RC phase shift network should consist of 180. Then 180, 180. Okay, if you add 360 degrees, we are going to get. Now, if you observe here, this is Vs and this is Vf. Both are in phase. Both are in phase. Yeah, we got. And that's why I said that the Barkhausen the phase, okay, between the phase difference or the angle between Okay, A and beta should be 360. Now take it. Okay, for this one, basic and the input is Vs. Okay, and RC phase shift of output is okay Vf. Okay, both are in phase. That's why Barkha criteria angle A beta is 0 degree phase shift or 360 degrees or n into integer multiple n into 360 degrees. Okay, now see here. This is a block diagram. Please keep in mind. Okay, here the basic basic amplifier consists of C amplifier. We know C amplifier consists of 180-degree phase shift. Okay, these points I explained here. Now, if you observe here, okay, this is okay. This entire part is CE amplifier. This entire part is CE amplifier. Please keep in mind. And means basic amplifier. Basic amplifier. Now I already said in feedback network. Okay, we are using RC. See here. This capacitor and R. This is a feedback network. Output is given as a input to here. Okay, in between that, this is a feedback network, positive feedback network. This is positive feedback network. This is feedback network. Feedback network. And this is amplifier. Basic amplifier. That is CE amplifier. That is CE amplifier. Okay, self-bias circuit. Self-bias circuit. Now, this C and R is there. Right? This C and R having the RC having the 60-degree phase shift. Here 60 degree, here 60 degree, here 60 degree. Together three, we are going to get 180. And this is 180, here 180, total 360 degrees. Okay, now this hybrid model we need to draw. For hybrid model, first to see here. Okay, this is okay HIE. Okay, generally we know that HIE is the okay hybrid model. We are having the four parameters HIE. Okay, input impedance, HRE, reverse voltage gain. Okay, HFE into IB. Okay, HFE is nothing but forward current gain and 1 by H naught. Okay, these four we can represent and output side. Okay, this is a load. Okay, then we have the capacitor and resistor. Capacitor and resistor. Okay. Okay, where we can take the output now? The RC, right? That's why this RC we need to consider. Okay, that's why here we are having capacitor and resistor. Yeah. Okay, this is okay. You do one thing. Same thing you can draw here. Okay, this is correct. Yeah. RC capacitor resistor, capacitor resistor, capacitor resistor, and we have to take okay this entire one. Okay, we need which one output side only. Okay, this one output side. This one I'm going to consider. And we know that R where we are going to give R we are giving to the input right. Then what it means across the R we can take it as a VF format. Okay, VF that output we are giving as a input. That's why we can consider as a VF here. Okay, convert into the Thevenin's theorem. Why it is converted into Thevenin's theorem? See here. This is current source. Okay, with the parallel of RC. This is nothing but neutrons. Neutrons. Okay, current source with resistance. Okay, HF into IB into RC is a voltage and RC. And if you apply that, you see, up to here you can write. Nowadays they are asking 5 marks question. Everything is 5 marks question. Nowadays they are asking 5 marks questions. Please keep in mind. For 5 marks question, up to here you can write. If they ask 5 mark question, then okay, calculating the frequency is there, right? Directly. Okay, if you apply the loops, okay, loop equation, these are, but you can remember this equation directly. You can write this equation directly, this one. Okay, for 5 marks they are asking. Okay, 5 marks only. Don't waste the time. Okay, for 5 marks. Okay, for okay 5 marks. Directly remember this equation. In this one, this is a real part. This is a real part. Okay, this is real part. I will take another color. Okay, then it is easy to. Okay. This is real part. Okay, this is imaginary part. Now imaginary part equal to 0. Okay, this one you can remember to find the frequency of okay r square xc plus 4 into r into rc xc minus xc cube. From this xc cube we can write this side. Okay, xc is the, okay, here xc if you take common from this, here xc and here one time it will get cancelled, xc square will get, xc square, okay, square if you send this, a root will get, xc plus 1 by 2 pi fc I can write, fc or f is equal to, I can write as a 1 by 2 pi, fc send this one you can send it here, 1 by 2 pi c into root square, inside this r square you can take common, r plus 4 rc by r. Okay, from this, okay, if your r square is there, if you bring into the outside, next square and root will get cancelled for r square. Okay, then r 2 pi, okay, 1 divided by 2 pi rc, root of 6 plus 4 into rc. This is the formula for solving the problems. Please keep in mind. This is the formula. Okay, if rc is equal to r, this will become 1, then 6 plus 4 is root 10. And equivalent to real part equal to 0, they are going to get, this is the condition for oscillating. Okay, based on this they ask one time question. This is, okay, problem. Okay, this is about the RC phase shift oscillator. Next one is Wayne bridge oscillator. Okay, this is also low frequency. Feedback method definitely consists of RNC elements. Okay, block diagram of Wayne bridge oscillator, they given that. Here two amplifiers they are going to use now. Two amplifiers. This is fixed bias amplifier. It consists of 180-degree phase shift. Here also self bias, here also it consists of 180-degree phase shift, total 360. Then here 0-degree phase shift. Okay, because this is a individual without feedback. Okay, without feedback, this is a consists of 360 degrees. Then beta consists of 0 degrees. So angle between A and B should be, okay, 0 or 360 degrees. Okay, that points we written here. Okay, you can take it. Okay, now fixed bias circuit, output of here coupling capacitance will be, coupling capacitance can be used for, okay, connecting between one circuit to other circuit. Okay, now this output is given as input to here, and here we are going to use, okay, which one, this is a self bias circuit, and this output is giving as an input to here. Okay, here they are going to use Wayne bridge. Okay, here bridge circuit I need to take. In the bridge circuit, definitely RC components should be there. Here R1 and C1, R2 and C2 parallel. Okay, here it is in series, it is in parallel. And R3 and R4. Okay, this is the Wayne bridge circuit. This bridge circuit, when they said this is a balanced circuit. Okay, and here coupling capacitance definitely. Okay, either you can draw here. Okay, one time you can draw. Okay, either you can draw here or here. Okay. Now, okay, in Wayne bridge oscillator, we need to do the analysis. To do the analysis, you can take the bridge circuit. Okay, in the bridge circuit, where you can consider output now. VF I can consider from here to here. From here to here. Then you can take this one. Okay, this is the output is V0 because, sorry, input is V0. For this one, input is V0 here. We are going to take, sorry, here V0 will be there. From here we can apply V0. Okay, sorry, from here to here VF. This is a VF, sorry. Okay, now, okay, R1 C1 series. Okay, where it is connected to series, here it is V0. Here it is a V0 and here it is VF. Okay, this is in parallel. Then to easy of analysis, this R1 and C1, okay, is in series, we know that time. But you can, the equivalent one you can take it as a Z1. Z1 is R1 plus 1 by J omega C1. Z2 is, this R2, C2 are in parallel. Yes, this is the parallel. Okay, the equivalent circuit. Okay, the equivalent impedance I can take it as a Z2. Okay, now we know that this is like a C voltage division rule. I need to find the VF. Okay, I need to find the VF. VF is equal to, what you can write? Okay, voltage drop across VF equal to total. Okay, the total voltage applied here V0 into, okay, VF across the impedance is Z2. Okay, V0 of Z2 by total impedance Z1 plus Z2. And we know that beta is equal to VF by V0. From this one, VF by V0 is equal to Z2 by Z1 plus Z2. We know that. Okay, what is Z1 and Z2? Okay, you can substitute here. And if you manipulate here, if you take LCM and all, okay, if you manipulate here, okay, we are going to get R j omega c by 1 plus j omega rc whole square plus R j omega c. From this, if you can expand it as a plus b whole square, okay, then we are getting beta is equal to R, okay, j omega c by 1 plus 1 plus j omega rc plus omega rc whole square. We know that A beta is equal to 1. A beta is equal to 1. Is it correct? The maximum of A beta is equal to 1. Now beta we find out. From this, okay, A beta value I substituted here. From this, I'm going to get, okay, this expression. This is important. This expression we are going to get. Okay, if they ask you 5 marks, you can just take it, analysis, okay, up to somewhere, and you can write this one. There are also real part and imaginary part is there. Here, real part you can equate to 0, okay. Then we are going to get f value. F is equal to, okay, what we are going to get 1 by 2 pi RC. Okay, based on this, they ask a lot of times problems. And next one is imaginary part equal to 0. Okay, we are going to get beta value. Okay, a is equal to 1 and beta is equal to 1 by, sorry, a is equal to 3 and beta is equal to 1 by 3, that a beta is equal to 1. Okay, this is about the low frequency oscillator using BJT. Same thing we'll discuss by using the FET also. Okay, high frequency oscillators. High frequency oscillator, I already said that in feedback network consists of LC tank circuit. Okay, this is a LC tank circuit. Okay, we know that resonant frequency F is equal to what you can get, XL is equal to XC of resonant. Okay, F is equal to 1 by 2 pi root LC. Please keep in mind. This is very, very important. Okay. Now we'll go for the Hartley oscillator. In Hartley oscillator, we already know that the basic amplifier will be their self bias and positive feedback network. Okay, positive feedback network LC tank here. Now it consists of 180-degree phase shift. Here also consists of 180. Total is 360-degree phase shift. Please keep in mind. This is the circuit. For oscillator feedback network, two inductance circuits are there, L1, L2, and capacitors. Okay, analysis. Now this feedback network, you can take it. Here input is V0, output is Vf for feedback network. See. Okay, this is a input V0, output is Vf. Now here I am going to give the nodes. So this is a node 1, node 2, and node 3. Okay, this one I can write in this fashion. See here, I can draw it down. See, node 1 is connected to Vf and inductor with the ground. Yes. Okay, this is a node 1. Okay, now I'm going to change. This is 2 together, node 2. This is node 3. I change it or not. Take it. Node 1 and node 3 connected capacitor. Yes, it's connected capacitor. And node 1 and node 2 is connected inductor. This is node 2, I said, 2 grounds. And this inductor is 2 and 3. Yes, 2 and 3. 2 and 3. Now it is look like I can change like this. Okay, this ground, I can take it as a comma. I can change like this. Now based on this, okay, L1 and L2 are, L1 and L2 are in. Okay, L1, L equivalent is equal to, the same current can be flowed here. Okay, L1 and L2 I am speaking. Okay, and the capacitance I am not comparing. The capacitance with respect to inductor parallel, but L1 and L2 are in series, same current only flow. Okay, that's why I can write L1 plus L2 plus 2M. 2M is a mutual inductance. Okay, then we know that, okay, in place of L1 and L2, I can write as a L equivalent. Okay, L equivalent. We know that the tank circuit is like a tank circuit, C and capacitance. X is equal to XL. Okay, then I am going to get L plus what we can write now here, L equivalent. Then 1 by 2 pi into root of L equivalent into C. What is meant by L equivalent? Now I said that both are in series, L1 plus L2 plus 2M. I can write. This is about the, okay, Hartley oscillator. Colpit oscillator. Okay, Hartley and Colpit oscillator, what is the difference? Is here two inductors and capacitor. In the place of inductor, here two capacitors are there and one inductor. And same way, okay, we have basic amplifier is CE, positive feedback network, we are going to use LC tank. Okay, now see here to calculate frequency, same thing. Here node 1, this is node 2, node 3. Here also this is, okay, node 1, this is node 3, and this is node 2. Now I change the circuit. Here capacitors both are in, okay, series. When it is in series, we know 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Okay, that is C equivalent. Okay, what C equivalent equal to, I can write, okay, C1 C2 by C1 plus C2. Okay, I can write in this fashion also. C equivalent. C equivalent is C1 C2 by C1 plus C2. Okay. Now see here, this is also look like a, this is C equivalent. This is C equivalent. Okay, X is equal to XL. Okay, same way. I'm going to get F is equal to 1 by 2 pi root L into C equivalent. C equivalent plus I can substitute this. Okay, these all are the circuits. Okay, we use BJT only. These all circuits we can discuss about with the FET. with FET. RC phase shift oscillator using the FET. Okay, RC phase shift oscillator, low frequency only. So using the FET. Okay, when we use the BJT, we used as a C amplifier is self pass. Here we have to use CS amplifier. CS amplifier. Okay, the CS amplifier we need to use. Okay, the CS amplifier is a voltage divided circuit. Voltage divided circuit. Okay, this is a voltage divided circuit, and the remaining is same. The circuit is going to be changed. Here, FET circuit will get amplifier in the place. Okay, previously in the BJT set bias. Okay, here voltage divided bias. Voltage divided bias using the FET. Okay, the circuit will come. Here also this is 180-degree phase shift, and here also 180. Total is 360 degrees. They both are same only, but here FET we are using the BJT. But analysis little bit change. Okay, now the analysis is okay. Directly I can take it as a V naught. This output is V naught, and this feedback network only I'm going to consider. Okay, same way. Here you can apply the loop equations. Okay, you can remember directly this one. If they ask you for 5 marks, you can remember this one. Okay, to find here for oxy oscillators, okay, you have to imaginary part equal to 0, then minus xc plus 6 into xc r square. From this, xc equal to root of 6 r square will get fc plus 1 by 2 pi fc into root 6 r square. Then fc is equal to then fc is equal to 1 by 2 pi rc into root 6 we can get. Root 6 r square will get. Like r square, if you r square and root will get root 6. Okay, there we got f is equal to 1 by 2 pi rc into root 10. The root 10 before 6 plus 4 into rc by r. Rc and r will be equal. The root of 6 plus 4 is root 10. Here it is root 6. Please keep in mind. Okay, this is about okay. RC phase shift also using FET. This is RC phase shift oscillator using FET is completed. Now when the oscillator using the FET. Same thing here also. Basic amplifier circuit. Okay, there are also two amplifier circuits are there. In BJT we used the fixed bias and here we used in self bias. Here we are going to use the CS amplifier with the fixed bias and the voltage divider bias we are going to use. Okay. Now this is the fixed bias. And this is voltage divided by it is not there now. This part is not there. Okay, this part is not there. Okay, only this one. Okay, wait a second. I will, okay. Yes, this is it. Now, see here, the analysis is here same as here the analysis is same as node. Okay, you can take from the circuit will change. Analysis is same as Wayne bridge oscillator using BJT. Using BJT. Please keep it in mind. And here also Hartley oscillator. Okay, here we know that the circuit okay will change. Okay, analysis is same. Call it also. The circuit will change here. Amplifier circuit will change. Same analysis. Okay, next one is okay. These all are the formula we got. Okay, RC phase shift oscillator. Okay, frequency, and this is a very important. When RC is equal to R, we'll get this one. And HFE. One time they asked that HFE. HFE is greater than or equal to 29 times. We have to get RC phase shift oscillator using FET also. When with the oscillator using BJT or FET, this will be the same. Hartley oscillator using BJT or FET, the formulas all are same. Colpit oscillator also formulas are same. Then they ask the question. Okay, like this question, they ask 2 marks. Please keep in mind. 2 marks questions are very important. Okay, they will give R and C. Okay, then we have to. They can ask that the minimum current gain they ask, and also frequency. Two things they ask. When they are given R and C, okay, for which oscillator this is phase shift, RC phase shift oscillator, RC phase shift oscillator, and they didn't mention is okay, it's a BJT or FET. Okay, then you can take it as a BJT. Yeah, wait a second. They given RC, right? Yeah, I understand. They given RC. Yeah. If they given RC, what it means? It's a definitely with the BJT. Definitely with the BJT, because we can get in the equation root of 6 plus 4 into RC by R. Okay, that's it. Substitute we can get this one, and HFE they asked. HFE they asked. Okay, you can check the problem. These all we solved in the classroom. Okay, next one is crystal oscillator. Is it? Crystal oscillator. Okay, in a crystal oscillator, crystal is used in the feedback network. Okay, that's why it is called as a crystal oscillator. The crystal is worked based on okay, inverse piezoelectronic effect. Okay, electric effect. Inverse piezoelectric effect. What it means? Generally, piezoelectric effect is nothing but okay. Inverse I will take first. What it means by piezoelectronic? Okay, in piezo, in piezoelectric. Okay, uh, if you apply uh, if you apply any vibrations, wait a second. Actually, if you apply, if you do any vibrations in the form of sounds, okay, if you give pressure something, okay, there is a electrical parameter like voltage and the current conversion is there. But inverse in the sense when you apply voltage electrical parameter, then the vibrations will occur. That is the inverse feature. Feature means from vibrations to okay electrical parameter voltage or current waves. Okay, inverse piezo in the sense it reverse. If you apply voltage or current parameter, vibrations will occur. Okay, that I explained here. Okay, types of crystal we can use quartz, Rochelle. Okay, there are different types of it, but quartz is very important among it. This one is a quartz. Okay, this is a quartz symbol. Okay, this is a quartz symbol. Quartz symbol acts as a inductor in a tank. See here, please keep in mind. Quartz can act as a inductor in a tank. Please keep in mind. This quartz can act as a inductor. Now there are two types of circuits: series resonance crystal oscillator, parallel resonant crystal oscillator. Now basic amplifier we need to use okay tank circuit, but crystal we need to use crystal. Okay, and it is a series resonant in the sense crystal is connected in series. Crystal is connected in series, and you can note down this crystal act as a inductor. Okay, these are we know C amplifier comes a 180-degree phase shift. Okay, now this is a again self-biased circuit using BJT. And here, series in the sense crystal and okay, capacitor. Crystal and capacitor in series. Analysis we know. Okay, whether it is inductor or capacitor or series or parallel, whatever it may be, the resonance frequency of how much you can get XL is equal to XC. Sorry, here XC is equal to XL. X is equal to XL. Okay, we know that. F is equal to what you can get to 1 by 2 pi root LC. Parallel resonant crystal circuit in the sense the crystal is parallel. Crystal is parallel with the two capacitors. Okay, this looks like which one now? Two capacitor in the sense it is like a Colpit oscillator. Colpit. For the Colpit oscillator, this what is the analysis same thing. But here inductor can act as a capacitor. Inductor can be act as a capacitor. That's it. This is about the okay crystal oscillator series and parallel. See series in the sense okay crystal oscillator along with one capacitor it is series. Then we'll get the same analysis. Okay, parallel in the sense two capacitors. It is like a Colpit only, two capacitors, but here crystal will be the inductor place. And we know the crystal can be acted as an inductor. Okay, these are the previous JNTUA questions. If you need, you can do it. Okay. Now, one time they asked that analysis of generalized equation for LC oscillator. Okay, I said very simple way. Actually, there are lengthy ways there, but I said I explain all LC tank circuits. What was there? Hartley, Colpit with BJT effect and LC okay, crystal oscillator. These three are there. Okay, these three we have to analyze I say I've taken it as a basic frequency of resonance. Okay, basic of that equation we solve this one. Or in another way also we can solve. But for that one, generalized equation of LC oscillator, they asked one time. Okay, for the generalized equation for LC oscillator, okay, here cell bias circuit will be there, and we know that Z1, Z2, Z3. If it is a Hartley oscillator, okay, Z1, Z2 are the inductor and Z3 is capacitor. If it is a Colpit oscillator, Z1, Z2 are the capacitor and Z3 is inductor. If it is a crystal oscillator, we know that Z1, Z2 are the capacitor, Z3 is the crystal. Okay. Now this one you can draw it as a, okay, you can take it as a hybrid model of the transistor BJT. Okay. We know that HIE, HRE, reverse voltage gain, and HFE IB, reverse voltage gain, HFE IB. Okay, 1 by H naught. And we need to apply the feedback. We need to apply the feedback. This is we can apply in the feedback. Okay, here Z1, Z2, and Z3. Here we need to, okay, we have some assumptions are there. HRE is a reverse voltage, right? Reverse voltage gain. This is very, very small. Okay, then we can neglect HRE and also, okay, 1 by H naught, 1 by H naught, output admittance. Okay, these two you can neglect it from the circuit. Then here we can get short circuit. Here we can get, okay, here we can get short circuit. The short circuit consists of, wait a second. Yeah, this is the value we can neglect in essence. Reverse, right? Okay, here minimum current will be there. Okay, current and here it is in opposite direction. Okay, you can take it as an open circuit here. Okay, then neglect this one. We can get this equation. See here it is a short. Here it is a open. Yes, it is a open. Okay, now we need to find. Okay, we need to find. Okay, this one to find these step by step. Now, first we need to find ZL, open loop gain, beta value VF by V naught, and A into beta. Okay, when we can do the A into beta, we'll get the generalized equation. First ZL we need to find out. Okay, ZL we need to find out. How we can get ZL? See here. I can circuit. I can minimize it. Z1 and HFE. If you observe here, current is going to be divided here. Current is going to be divided. Current when it is going to be divided, what it means HIE and Z1 both are in parallel. Okay, then I can write the equivalent resistance is, sorry, the equivalent impedance is 1 by Z dash. I am going to take it as a 1 by Z dash. 1 by Z dash is equal 1 by Z1 plus 1 by HIE. If you take LCM, if you take it reciprocal, Z dash is equal, we got this one. Now, these two place, okay, these two place, I can take it as a Z dash. See here? Yeah, Z dash I can take. Now, if you observe Z dash and Z3, Z dash and Z3, I am going to minimize because ZL I need to find out. Okay, Z dash, Z3 are in series because same current is flowing. Okay, same current is flowing. Z dash and Z3 are in series. Then the equivalent resistance is Z double dash is equal Z dash plus Z3. Z double dash is equal to Z dash. I substitute here. We already find out Z dash is what is the value. Yes, I substitute here. Okay, then the equivalent circuit is these instead of these two, I can take it as Z double dash. If you take Z double dash, I can get this expression Z double dash Z2, and it is the current gain. Okay. Now, if you observe Z2 and Z double dash both are in parallel because see here current is going to be divided. Or not? Yes, current is, if you see in this way also, current is going to be divided. In this way also, current is going to be divided. If current is going to be both are in parallel. Then 1 by ZL. Now 1 by ZL I can take last. Okay, I can take equivalent circuit 1 by ZL is equal 1 by Z2 plus 1 by ZL. If you manipulate this, okay, if you see, you get ZL is equal to this. You have to remember. Please keep it. Okay, ZL is equal to, how to remember? See, Z1 into HIE, Z3 into HIE, and Z1 Z3. You can get common of Z2. And HIE of Z1 plus Z2 plus Z3 plus Z1 Z2 plus Z1 Z3. Okay, this is very important. You have to remember the Z1. And after that, I need to find out the open loop gain. Okay, open loop gain in the sense what it means without feedback. I didn't apply any feedback. AV is the open loop gain. This is open loop gain. Open loop gain. Okay, open loop gain I'm going to find out. For open loop gain, we know that, okay, because here minus indicates C amplifier consists of 180 degree phase shift, output consists of minus. That's why AV is equal minus of V naught by VA. Okay, from this minus V naught is, okay, where it is going to be the current flowing through the ZL is V naught. Then minus HFE into IB into ZL. This is the current, right? Minus HFE into IB into ZL. V naught plus HFE IB into ZL. This is a resistance impedance, and here it is the current is going to be flow. Okay, Then AB is equal to minus HFE IB into by ZL VI. VI is what is the VI now? VI is the IB into HI. IB into HI. IB will get cancelled. AB is minus HFE into ZL by HI. Next beta is equal to VF by V naught. VF by V naught I'm going to find out. For VF by V naught, okay, I'm going to find out in this way. Okay, this is a VF. VF is where we are going to get VF. I'm going to get across the uh, VF. I'm going to get across the Z dash. This is Z dash. Sorry, not Z bar. This is Z dash. This is Z dash. Okay, Z dash. Okay, here the feedback network consists of a 180-degree phase shift, right? That's why, okay, VF is equal to minus I into Z dash. What is Z dash? We know. Okay, we already find out Z dash. Okay, next V naught is equal to, from the feedback network, V naught is equal to, these are with the feedback. Okay, V naught is equal to minus I into Z double dash. Minus I into ZW. Because why? Okay, Z2 and ZW both are in parallel. I can get the same voltage. V naught I can take at the Z2 or Z double dash auto exchange. For Z double dash we know that. Z double dash we already find out that. Okay, this is minus I. Why minus in the sense I already said that. Okay, V naught consists of 180-degree phase shift. 180-degree phase shift. Wait a second. Okay. Now, Z double dash is substituted in this equation. Okay, after substituting Z double dash, okay, we are going to get this equation. Okay, from this, okay, V naught we find out. V naught we find out. Beta, okay, beta is VF by V naught, right? Okay, for that VF we find out and V naught we find out. Then beta is equal to, then beta is equal to, okay, then therefore beta is equal to, I can write V naught, okay, sorry, VF by VF by V naught. Okay, then we know, just now we find out here minus minus we get cancelled. If you do some manipulations here, beta is equal to, I can get this one. AB into beta is equal to 1. For that AB into beta is AB we already find out, open loop gain into beta. Okay, if you manipulate this, this is a generalized expression. This is a generalized expression you have to remember. See here, this is very, very important. The generalized expression you have to remember. See, HIE into Z1 plus Z2 plus Z3 plus Z1 Z2 plus Z1 Z3 plus HFP Z1 Z2. This is very, very important. This is a generalized expression. Okay. Now we know that for Hartley oscillators, Z1, Z2, Z3 are what we know. Two inductors are there, one capacitor is there. These equations, if you substitute here, we will get that answer. Okay, that is frequency and F is equal to 1 by 2 pi. Okay, root L equivalent into C. L equivalent plus what we can write. Okay, C, L1 plus L2 into 2. Okay, this is about the oscillators. This is about the oscillators. This is general equation they ask. Okay, final conclusion is listen carefully. In this chapter, we are going to study about, okay, totally, okay. There are 6 circuits are there. What is that one? First one is, okay, RC phase shift. RC phase shift with BJT and FET. Okay, for this analysis is different now. Okay, analysis is to find F. Okay, for this F is 1 by 2 pi RC into root of R into C, not RC. R resistance into capacitance into 6 plus 4 into RC by R. 4 into RC by. For this, F is equal to 1 by 2 pi R into C into root 6. This is different. Means analysis is different. For Wayne Bridge, this is the important thing. Okay, for FET and BJT, analysis is different. Okay, analysis is different. For both, analysis Analysis is different. Is different. Circuit also different, but we know this is using BJT and FET. Now this is two circuits you can use. There are two circuits. And here Wayne bridge oscillator. Wayne bridge oscillator. Oscillator. BJT and FET. BJT and FET. In the BJT and FET, okay, using Wayne bridge oscillator, circuits are different. Analysis is same. Here analysis is different. Okay, here analysis is same. Analysis is same. Circuits are different. That we know using BJT FET when we said circuits are different. Next, Hartley oscillator. Hartley oscillator. Hartley oscillator. Okay, next Colpit oscillator. Colpit oscillator. Or else I will tell commonly now. Colpit oscillator. For these are using BJT and FET. Analysis is same. Analysis is same. Please keep it. Okay, circuits are different, but analysis is same. That's it. Okay. These are if you study, and the extra thing is crystal oscillator. Crystal oscillator. The crystal oscillator is crystal ergotally that is same as Hartley oscillator, Colpit oscillator one time, and this is the basic answer. Crystal oscillator is series and the parallel. Okay, series and parallel is there. That is somewhat different. Okay, but okay. How come circuit check it? 1, 2, 3, 4, 5. And the sixth topic is which one now? The sixth topic is generalized equation of LC circuit. Generalized equation. Generalized equation of LC circuit. LC oscillator. LC oscillator. Last one I said, right? Okay, that. These six topics, if you study, this part is over. Definitely one, two more question. Okay, one question is 10. Okay, these six topics you can study. Thank you.